Welcome to this video on radical equations. Before you start, there are two videos that you might want to check out before you try to watch this one. One's called Quadratic Equations, Part 1 of 4, and another one is called Radical Algebra. If you're not sure whether you need to watch these videos, here are two different math problems, one from each video, that you can pause here and analyze whether you have the math skills to continue into this video, or whether you need to go back and see one or both of the previous videos that lead up to this. But assuming you're ready to get started, here we go. First, I want to start with a basic idea that's prevalent throughout this whole video. Suppose you have a radical of some number or algebraic expression, and you're squaring that radical. Well, to square something means to multiply it by itself, and whatever this expression is when multiplied by itself would be that expression squared. And so now we're left with radical expression squared, and the idea here is this is asking us for that number or that expression which when squared is some expression squared. Well, of course, that will be the expression itself. And if I've lost you in some generalities here without giving a specific expression, you'll see how this basic idea works throughout the rest of the video as we go. Here's our first actual example of a radical equation. Now suppose we're trying to solve this equation for x. Some people can solve this equation just by looking at it, by determining that x would have to be 23. If you're such a person, you can see why 23 would work. If you don't think that way, don't worry. There's a strategy that we can use here. The strategy is called squaring both sides of an equation. It's a great strategy for solving radical equations because if properly formatted, squaring both sides of an equation can make it simpler and eliminate the radical. In this case, the expression on the left squared, or the radical squared, is the radicand itself, using the basic idea that we just saw. And by squaring both sides, you can eliminate the radical and have a basic enough equation to just solve it using ordinary algebra. Here's a slightly more complex example. Now, one might think that squaring both sides would get rid of a radical. You're allowed to square both sides here, but this is a horrible idea. Why? Because the expression on the left, inside of the squared, becomes very, very messy when we multiply it by itself. Restated, the squared and the radical there don't cancel each other out, because of the amount of algebra that we would have to do to square that thing. So rather than square both sides, what we're going to do is isolate the radical. We're going to do whatever algebra is necessary to get the radical by itself, because then we can square both sides. So to get the radical by itself, the first thing I did here was add 6 to both sides. Further, to isolate the radical, I divided both sides by 2. Now, what I've done is I haven't solved for x, but I've managed to do just enough algebra to get the radical by itself. And now that the radical is isolated, now is the perfect time to square both sides. Because with the radical isolated, look at the left side of the equation as I say this, the square root of any expression squared is the radicand itself. And of course on the right, 3 squared is 9. So you see, by isolating the radical and then squaring both sides, I've reduced this complicated equation to a simple algebraic one, which I can solve with very little effort. And now I have the solution to this equation. But we need to take a brief detour into something called extraneous solutions. To understand what that is, I'd like to point out that on the previous two problems, we got to a point where we could square both sides, thereby eliminating the radical. And we didn't make much mention as to whether that's always a viable option. But it turns out something unusual happens, or can happen, when you square both sides of an equation. And to show you what can happen, we're going to look at this example here. Suppose I were to square both sides of this equation, thereby canceling the radical, and did some algebra and solve for x. Don't worry about this particular algebra here. This isn't one of our main examples, but the purpose here is to look at what can go wrong. If you'd like to pause and do the algebra, you should have that ability. It's not a big deal. The point being, if we take 5, one of our solutions, shouldn't we be able to plug it back into the original equation and get a true statement? That's the very definition of what a solution is. Well, it turns out that 5 is a solution here because when you plug 5 into the equation, you get a true statement. 5 equals radical 25. Now, we've often been taught that we should plug our solutions back into equations, but generally we're taught that because we're trying to catch our own mistakes. In other words, if we plug a solution back into an equation and it doesn't work out, we're to assume that we made an algebra mistake and thereby have discovered a wrong answer, one that was caused by our own error. But the notion of extraneous solutions, which we're getting to that idea here, is that you can get an answer that when plugged back in doesn't check out, even when you didn't make any algebra mistakes whatsoever. And squaring both sides of an equation can cause that to happen. Now we know that 5 is a solution because we've checked it out. Watch what happens when we plug -3 back into the original problem. If you do the math on this, you'll get something that isn't a true statement. -3 equals radical 9 is not true. Radical 9 is +3. The conclusion, therefore, is that -3 is not actually a solution to this equation. So to summarize, whenever you square both sides of an equation, it's possible that one of the solutions or both of the solutions you get aren't actually solutions at all. And when that happens, we don't mention them. We simply say the number that is the solution. Some students have a tendency to say that in this problem, 5 is a solution and 3 isn't. But we don't mention things that aren't solutions. 72 isn't a solution, nor is 41.6. We didn't mention that they weren't solutions either. So resist the urge to say that 5 is a solution and -3 isn't, because we don't mention things that aren't solutions. This equation has one solution, and it's x equals 5. Here's another example that's going to turn out to have what's called an extraneous solution, which isn't a solution at all. Now, on this problem, to solve, it would be smart to isolate the radical. So I'm going to subtract 9 from both sides. And now that I've isolated the radical, I can square both sides. On the left of my equation, the radical squared is the radicand, and on the right side I use the FOIL process to square x minus 9. Now the good news is I no longer have a radical in my equation, but I've created a quadratic equation that needs to be solved. You may recall that quadratic equations are solved by setting them equal to 0. So here I subtracted 3 from both sides, and now I'm going to subtract x from both sides. The purpose being, quadratic equations should be set to 0. Now at this particular point, the polynomial on the right factors. Most people don't have memorized that 13 times 6 is 78, but it is a factorization here nonetheless, which leads us to two solutions, x equals 13 and x equals 6. Or perhaps we think we have two solutions. It turns out one of them doesn't work, because when we plug in 13 to check for extraneous solutions into the original problem, we get a true statement. But when we plug 6 into the original problem and crank out all the math, it leads to the statement 12 equals 6, but 12 doesn't equal 6. Therefore, that's not a solution to this equation and should be ignored. Now, we could say that x equals 6 is an extraneous solution, but since it really isn't a solution to the equation at all, there's no sense mentioning it in the final answer, and we simply say that x equals 13 is the solution to this equation. Now let's look at the most complicated kind of radical equation that we generally encounter, one with two radicals in it. You may recall that we normally start by isolating a radical. Well, you can see that one of the radicals is isolated and one isn't. I could square both sides right now, but I've found over the years that I have more luck by isolating the complicated looking radical. And so I'd like to isolate radical 2x minus 2 by adding 1 to both sides. You don't have to do this, but it turns out to be less algebra, I have found, if you isolate the uglier looking radical and then square both sides. Now on the left side of this equation, I have radical expression squared, which leads just to the expression from the basic idea we saw earlier. But on the right side of this equation, the square doesn't cancel the radical. Think of it as the radical not covering the entire inside of the parentheses, if you will. And so when I square the right side, I end up getting something else. I don't expect the typical student to see where I got that, so you may want to pause and examine the work here. It's basically just FOIL. But I've created a problem for myself in a way. I've squared both sides, and I still have a radical. In some sense, I've made progress because the original equation had two radicals, and now I only have one. So my plan now is to isolate that radical. So I'm going to subtract 1 from both sides. And now to further isolate the radical, I've decided to subtract x from both sides. And if I really wanted to be technical here and isolate the radical, I should divide by 2. And it wouldn't be wrong to do that, and it would be useful if you wanted to make use of it, but I have a way of avoiding fractions here. Now, even though we haven't isolated the radical, we have isolated the term that has the radical in it. That's usually good enough to square both sides. On the left side of the equation, I used FOIL to square x minus 3. And on the right side of the equation, I ended up with just 4x. Here's the work if you want to pause and ponder that. So after isolating a radical, squaring both sides, isolating the new radical, and then squaring both sides again, I now have a quadratic equation without any radicals at all. And assuming you have knowledge of quadratic equations, subtract 4x from both sides, factor and solve, this shouldn't seem too difficult to finish this up. So now I should check for extraneous solutions. By the way, up till now, you might have gotten the impression that whenever there are two solutions to a radical equation, that one of them turns out not to work. Well, that's not always the case. Let's see what happens here. I'm going to check for extraneous solutions by plugging 9 into my original equation. And when I did all the math on this, and I didn't show it in the video, but when I did all the math on this, I got 3 equals 3. That's a true statement. And that indicates that 9 is in fact a solution. Now let's check x equals 1. When I plug 1 into the equation and do all the messy arithmetic, again, not shown here, The end result is a false statement. -1 doesn't equal radical 1. Radical 1 is +1, not -1. That means that x equals 1 is not a solution to this equation. And once again, we're in a situation where one of the two solutions turned out to be a non-solution, leaving me only with one. And while this video doesn't show such an example, there are examples of radical equations that have two valid solutions, so it definitely can happen. This is about as messy as it gets in the world of radical equations. And that completes the lesson on radical equations. Thanks for watching.